My name is Zhang. I'm with Group 4, presenting on experiment number 6, the air conditioner or commercial air conditioner. So this is the outline of what my presentation will cover. So first, a little introduction. The goal of this lab is to get us familiarized with the commercial AC, and also to get familiarized with the equipment and the controls, parts, and also the program that we would use to calculate stuff for a commercial air conditioner. For this lab, we're focused on the variable air volume AC. That's just what it's called. It's a little theory, pretty much it's a very simplified concept. We got hot air coming in, goes through the cooling coil, it gets cool. And that air leaving is colder, but when it gets to the fan, the heat from the motor will raise it by like a slight 1 degree maybe. And how it ties in with our thermodynamics is pretty much, it's a refrigeration cycle. I'm pretty sure we got enough explanation for that, but pretty much it goes from 1 to 2 by being compressed up, ideally isotropically. And then it goes from isobar from 2 to 3, but they broke it into 5 parts, but 3 right here. And then it gets cool, and then pretty sure you guys heard this enough. The objective for the reporter, anyway, is to calculate the different efficiencies. There's the CBF, which is the coil bypass factor, and the EER, which is energy efficiency rating, and the COP, which everybody knows is the coefficient of performance. There's just a difference in how they're calculated. For the CBF, it's the leading temperature minus apparatus dew point divided by the entrance temperature minus the apparatus dew point, right? And the energy efficiency rating is the size of the unit. Size of the unit divided by the electrical input, and the COP is just the ER divided by this factor. Y'all mostly seeing how COP was calculated in the other projects. This one's just it's a conversion, not the actual equation for COP. So another objective, again, is to familiarize ourselves with the air conditioning, commercial air conditioner, like I said earlier, and also familiarize ourselves with variables in these equations. So here is the apparatus that we'll be using. It pretty much consists of 4 parts. It's a cooling loop, which has the AC, and it draws in the air, cools it, and goes to the supply air heater, which it's just for our experiments, just to heat up the air to a certain degree that we want. And it goes down here where there will be 2 boxes for chamber A and chamber B. They act as rooms. The only difference between chamber A and B is that actually somebody drew it over here. For A, it's right next to the hot plenum, which is the 4th part of our apparatus, which is just a closed loop that generates heat. And like the difference is for A, they share a wall. For B, there's actually an air gap, so that's just more thermal resistance. That's the only difference. So a little bit of the procedure. Well, first of all, safety first. Make sure you don't touch any ducts, insulation. You can burn yourself because they obviously get hot. Also, we don't want to turn on the heater before turning on the fan because we'll overheat the system and break something. And also, I guess, know things like where the fire extinguisher is. I don't really see one in this room. I know the fire alarm's outside. There's a safety shower here. I hope nobody catches on fire. And then also stay clear of electrical components. I guess it's just to avoid being shocked. So for our procedure, we start off by turning on the program on the computer. And from there, we actually control what we call the variable air volume component, which is just a actuator. It's just a damper that's controlled by a mechanical actuator. And we set a setting for that. We started the heating loop. While we wait for the heating loop to start up, we started the cooling loop. After that, we put in some more settings or change the setting back to what they're supposed to be for the valves again or dampers again. And then we wait about 2 to 3 minutes before it gets everything to equilibrate. And then the timing is very important. For the reporter, they need to record the data for every 20 seconds for 30 minutes. And that's pretty much what the procedure is. Here are some more equations. These are actually used by me to calculate the anticipated heat flow and volume flow. So what I did first was calculate the heat flow. I assumed, like Ben said, temperature difference. I used 95 and 65, so the difference of 30. And also 1 foot squared area divided by the thermal resistance, which was given in the lab manual. And then once I solved for Q, I used this equation. And since we there was assumed in our manual that they simplified this to 1.08 times the difference in temperature and volume flow rate. I don't have that up there, but it's in the manual. And then we just solve for the volume flow rate. Here's what I got. Again, the assumption is 1 foot squared for the wall, the temperature difference. So the total resistance for A, since there's no air gap, is 0.93 feet squared per Fahrenheit hour BTU. And obviously you can see that thermal resistance is higher for B because of that air gap. So therefore we get the heat flow for A is higher than B because again less resistant. And you can see that's what I guess calculated from the other formula because of the difference in heat flow. I mean the heat flow, we have a difference in the cubic feet per minute. And that's my sources. Any questions?